Okay, so now we come to the last presentation by a young researcher of the day. So Eduardo Alves da Silva, who is also a PhD student here at IMPA, and he will tell us about birational geometry of Calabi-Yau pairs.
So thanks, Carolina, for this opportunity to be here. Thanks for the organizers. So I will talk about birational geometry of Calabi-Yau pairs, which consists of the subject of my PhD work. So to start, we denote Pn as the project space over the complex numbers. And we call a Cremona transformation of Pn a birational self-map. And for n equal to 2, we say that such transformations is the Jonquières with it preserves a pencil of lines. And with the operation of the composition, the set of the Cremona transformation is a group, which is called the Cremona group is denoted by Bir of Pn. And the study of this group has been an active area in algebraic geometry. And for elements of this group, we have a factorization theorem, which is called the Sarkisian program, which is in its particular situation for Pn. We have that we can decompose every Cremona transformations into elementary links. This theorem is more general, and it asserts that for any birational map between more fiber spaces, we can decompose into elementary Sarkisian links. So let's consider C an irreducible plane curve, and the decomposition group of this curve introduced by Gizatulin is the group of the birational self-maps of P2, which will preserve this curve as a set. And the inertia group of this curve is the subgroup of the decomposition group, which will preserve this curve point-wise. Here we are doing some abuse of notation. Sorry. Here we are doing some abuse of notation because at first we could have some proper base points of this map contained of the curve. Okay, but we will have the answer for this question in the next slide. For using by adjunction systems, Pan was able to show that for any non-singular plane curve of degree greater than 3, every Cremona transformations that stabilize C is an automorphism. This result means that the decomposition group of this curve is just the linear automorphisms of P2, which will preserve this curve. Actually, my colleague also spoke this in another situation, but it's pretty the same. But what can we say about the decomposition in inertia group for the degree 3 case? Because the last corollary is about curves which has degree greater than 3. In the case of a cubic curve, we have the notion of Calabi-Yau pair. And this notion will allow us to use new tools to study these groups. But what is a Calabi-Yau pair? It's a pair consisting of a normal project variety and an effective reduced via divisor D on X, such that the sum of them is Cartier and linearly equivalent to 0. In other words, if you consider n as the dimension of the variety, there exists a volume form, omega, such that D plus the divisor of this volume form is equal to 0. And for Calabi-Yau pairs, we have a notion of volume-preserving map, which merely says that if you have x dx and y di Calabi-Yau pairs, a birational map between them will be volume-preserving with the pullback of the volume form associated to the divisor dy is a non-zero multiple to the volume form associated to the divisor dx, or where this pullback is induced by the birational map. And for the volume-preserving maps, we have a sort of generalization of the Sarkisian program. This theorem asserts that for any birational map between more fibered Calabi-Yau pairs, we have that this map is a composition of volume-preserving Sarkisian links. So it's a kind of Sarkisian, program with this additional structure. CK, Calabi-Yau. Oh, where? Is Conte and Calogeiros. Conte and Calogeiros. And now, if you consider C as an irreducible and non-rational cubic, we have readily that P2 and this curve is a Calabi-Yau pair. And by a theorem for Pan, if you have an irreducible non-singular and non-rational curve and suppose that there exists an element of the decomposition group which is not a linear automorphism. So Pan was able to show that the degree of the curve is 3, and the set of the proper base points is contained in the curve. So here we have an illustration of this theorem, and now considering a non-singular irreducible cubic, consider PQR 3 points not all collinear, and denote by PQR as the standard Cremona transformation centered in these 3 points. One can show that the image of this cubic by this Cremona transformation is another non-singular cubic, isomorphic to C. And we can also show that there exists a linear automorphism such that the composition of this map belongs to the composition group of the cubic. And we call a C-generic quadratic transformation as aberrational self-map of P2 of the previous form. And by a result by Pan, he was able to show that the composition group of the cubic is generated by elements of this type. And our first proposition is, for an element of the decomposition group, we have that an element of this group is a birational self-map of P2, and is also a volume-preserving map of P2 with this non-singular cubic. And what we were able to show is that when we apply the standard Sarkisov program in these conditions and over a suitable algorithm in order to have termination, we have that the Sarkisov decomposition is automatically volume preserving. So at first, we don't need to have this kind of feature. And the key idea for this is to note that all the surfaces together with the corresponding strictures transforms of C when we are applying this program are always Calabi-Yau pairs. And the possibilities for the application of this program, for this volume-preserving Sarkisov program, will depend on the nature of the intersection of the proper and infinitely linear base points with the fibrations of the corresponding more fiber space that I will meet along the way. And a corollary is that in the plane case, the Sarkisov program also gives us a decomposition of aberrational self-map into the Jonquier's transformations. And in this case, we are able to show that the centers of the Jonquier's transformations belong to the cubic and its strict transform. And our question is that we don't know if these points may coincide or not. Recall that the Jonquier's transformations will preserve a pencil of lines through a point. And when I was performing and studying this kind of subject, I noticed that the volume-preserving Sarkisov factorization of n element of the composition group of the cubic does not involve any elementary link with Fn with n greater than 2 and the domain and codomain. This Fn denotes the Hirzebruch surface, and it appears when we are applying the Sarkisov program. And how about the inertia group? For the inertia group, we have a result by Blanc that tells us that it's generated by the elements of degree 3, and except for the identity, such elements are of the lowest degree. And we have this exact sequence here, which was proven by Blanc and Ogiso. At first, we have a complex. The sequence is a complex. And what is not trivial in this exact sequence is the surjective of this restriction map, which Daniela also spoke in previous. Every birational map of the curve is derived from an element of the composition group. And Blanc, Pan, Yvest posed this question in some article asking whether this sequence is splitting or not. And one of our results is that this previous sequence does not admit a global splitting at the birational group or birational set of the birational transformations of C, because this group has has this description as the same direct product of the curve as ED, or where D depends on the J invariant of C. And if we have a splitting, we would be able to have a section for this group to this group. And since C is also an elliptic curve, is also an algebraic group and projective. So with this splitting that exists, we would be able to put this curve inside a subgroup of the plane Cremona group. And there exists a result that all the algebraic subgroups of the Cremona group are all of them are affine. And since our curve is projective, so we cannot have this I splitting. But maybe we can improve this result at I splitting in some subgroup of this group. And now we will deal with the three-dimensional case of my studies. If we regard the quark surface with canonical singularities, we also have readily that P3 with this quark is a Calabi-Yau pair. And our first lemma says that if you have a volume-preserving terminal divisorial extraction between Calabi-Yau pairs, contracting a divisor to a closed point in P3, so such point must be a singularity of D, and Dx is the birational transform in X. And by a theorem by Kawakita and suitable analytic coordinates at P, these divisorial extractions can be described as the weighted blow-up of P with weights 1AB, where these weights are all co-prime. And so the problem that I studied was to determine which weights will be volume preserving, because we can have some volume preserving maps starting by P3 with this quark surface. And so we would like to know which weights will initiate a volume preserving Sarkisov link. So I didn't tell you, but there are other two equivalent definitions of the volume preserving property. And one of them is based on some quality of some discrepancies. And for example, if we try to attack this problem at the first time, we would have to deal with this weight blow-up explicitly. So this is a little bit hard. Even the ordinary blow-up, if we want to analyze all the affine charts, is hard in the first moment. So we will use another description of the valuation associated to the discrepancy associated to the exceptional divisor of this weighted blow-up, which will be a toric descriptions. This toric descriptions is a finite sequence of ordinary blow-ups along points and lines, such that the last valuation will coincide with the valuation associated to the exceptional divisor of the weighted blow-up. And our lemma is that if we have a quark surface with an isolated canonical singularity, the weighted blow-up at P with coprime weights 1AB is volume preserving, with and only if each blow-up in its toric description is volume preserving. So this is a key lemma to get our volume preserving weights. So here we have a table summarizing our results that for the AN case. So we have here we have some possible volume preserving weights initiating by this quark surface. And here you can notice that we have some colorful weights, and these weights have this color because they will not work when we consider a coarse moduli space for the quark surfaces having this kind of singularities. These colorful weights will not work generically. So because the quark surface having such type of singularity must satisfy some closed conditions in the coarse moduli space. And so here we have some examples of links initiated by P3 and this quark surface. So the standard blow-up will work for any AN singularity. double up with weights 1, 1, 2 will give me, and the codomain, the weighted project space with weights 1, 1, 1, 2. And when applicable, the weights 1, 1, 3, these weights are volume preserving. This divisorial contraction here belonging to the first volume preserving link is also volume preserving. But the problem with these weights is that the codomain is not terminal. This weighted projective space that I obtain here is not terminal. And also, I didn't tell you, but in the Sarkisov program, and each step we require that all the varieties need to have terminal singularities. And this weighted projective space doesn't have terminal singularities because of these two here, which will imply that we have a curve of singularities. And dimension 3, terminality is equivalent to non-singularity in codimension 3. So since curves have codimension 2, this Calabi-Yau pair is not terminal. Here, here are the references for my work, and thanks for the station, and sorry for the hurry.